All right, everyone, welcome to Physics 220. So I'm going to start with chapter 1, which is on concept of motion. So we're going to cover this chapter and maybe a little bit of chapter 2 during the first day. And it's important that you guys always try to watch the videos ahead of time. I'm going to always try to give you a little more time, at least a couple of days before, the meetings, so you have a chance to watch the videos. And in general, those videos going to be kind of like your main source for the concept. That means I'm going to be covering everything here, doing all the examples, and you need to watch everything. And you have the option then to basically pause, go back, watch it again, or watch how I solve the problems, then go back, pause, and try to solve those problems on your own. But this will be sort of like something that I will not necessarily be going over during the lecture, during the Zoom meetings. So you will be watching this ahead of time, and during the Zoom meetings, I will be then summarizing some of these things. All right, so chapter 1 is basically introduces us motion, linear motion specifically. So one of the things we're going to be doing during the semester, we're going to be learning about, you can see in this image here, right, in this slide, different types of motion. Obviously, the simplest one is the straight line linear motion, and that's what we're going to be starting with. Then, as we learn more, as we get more comfortable with solving problems with physics concepts overall, we're going to be then extending that. So we're going to be looking at sort of like, let's say, circular motion, projectile motion, which is basically two-dimensional motion, right? And then rotational motion, which is a lot more complicated compared to linear motion. But obviously, as we get better, as we learn more, concepts, we, solve more problems, learn how to, approach physics problems, you will be more comfortable with a little more difficult, for example, concepts later on in the semester. All right, so generally what we're going to be doing here in this chapter, we're going to be learning some, some tools that are going to help us to solve, problems in, let's say, chapter 2. So chapter 2, where sort of like, let's say, problem solving starts. In this chapter is kind of like, let's say, here's this tool that you can use. Here's another tool. For example, this particular slide going to introduce us what we call a motion diagram. And then we're going to learn about, position versus time graph, something like that. So basically some tools that are going to be useful down the line. All right, so let's look at this particular slide. What we have here is an object. And generally what we have here is we're going to be taking, like, let's say, a car or a person or anything, like, let's say, there's going to be moving as, as our object. Here is the car. And what we do here is we look at the car as it's moving and we take pictures. And we make sure that every picture is taken exactly same time interval compared to the previous one. That means, let's say, we take picture every second. So that means the time interval between the frames then is going to be 1 second. And when we put those frames together, what you will see here is basically sort of like a movie, right? How the car is moving as a function of time. Because one of the things we have here is, then you can see that this one kind of shows the car at t equals 0. And then what we can say, okay, here's the position of the car, x initial at t equals 0. And this is then going to be t equals 1 second, right? Because 1 second later. And then this is going to be t equals 2 seconds, t equals 3 seconds. And then taking, for example, this to be initial position of the car, and we can always set that to, for example, 0. Then I can say, all right, so then this is at x1, which is t equals 1 second. This is then x2, t equals 2 seconds. And this is x3, t equals t equals 3 seconds. That means that's the position of the car as a function of time. That means every second, the car is further and further from our initial position. All right, so that again, so a movie camera takes photographs at a fixed rate. So let's say in this case, 30 photographs every second. Each separate photo is called a frame, and the car is in a different position in each frame. Okay, so that's why it's going to help us kind of like, let's say, analyze the motion of the car or of our object. All right. So the shown are 4 frames in the film strip. All right, so putting everything kind of together, then what we get here is an image like this. Okay, so that means what I can say here is this is the position of the object. So X initial, then this is X1, and this is, let's say, X2, this is X3, and so on and so forth. All right. I also want to make sure that, you understand which one is the starting, let's say, position in terms of when it happened at t equals 0. Okay. So then one of the things I can do here, I can say t equals 0 and 1, 2, 3. So generally at the top of the object, usually given sort of like the time in this case. All right. Okay, so this composite photo shows an object's position at several equally spaced distance of time. Okay. That means one thing we're doing here in terms of, let's say, that is exactly equal to one another is the time interval. That means we're making sure that from frame 1 to frame 2, this delta t is exactly same as the from frame 1 to frame 2. So initial frame to the frame 1, then 1 to 2, 2 to 3, and things like that. So let's say delta t1, delta t2, delta t3, right? That means we're making sure that those are the same, right? So those are the same time intervals. How much distance it will be covering during that same time interval, it's, let's say, doesn't have to be necessarily exactly equals to the same. All right, so it doesn't have to be exactly the same. So the time intervals are the same, but distance, for example, in this case, maybe you can see that this delta x1, by the way, delta, remember, is change, and when I put delta t means change in time, delta x means change in position and things like that. So here, delta x1, delta x2, delta x3, in this particular, for example, motion, you can see they're more or less are the same. All right, so they're more or less the same. That means same time interval and exactly same distance covered during those time intervals. And we're gonna see that this is a very specific type of motion. All right, so but in any case, so let's kind of get rid of this because I have some things over there. All right, so again, this type of tool that I just used to describe motion is known as a motion diagram. All right, so the motion diagram is a tool that we use to represent objects' motion as a function of time. All right, so an object that has a single position in motion diagram is at rest. So for example, if you have a ball and at t equals 0, it has the same position as at t equals 1 second, t equals 2 seconds, t equals 3 seconds. That means the position doesn't change. Then we can say that object here is at rest. So the stationary ball on the ground is at this point, for example, is at rest because it's not changing its position as a function of time. So that's why whenever you read a problem and it says object is at rest or object starts from rest, that means you can assume that, at the instant when you consider the object starting to move, at the instant at t equals 0, the object has no velocity or no speed. So, and what we have here is just like the previous slide that we talked about in terms of the object as it's moving, the distance between each frame, right? Or the distance from, initial time to the, subsequent, times, right? Is exactly the same. So then, for example, here you can see, right, a skateboard. So if I take this as X initial, or I can just say it's X1, for example, and this is X2, X3, X4. And then one thing you can see here is going from X1 to X2 is exactly same distance as from X2 to X3. And remember, the time is always going to be the same time interval, right? That means we're always going to assume that it's exactly, same time intervals. Could be 1 second intervals, could be 5 second intervals, but going from one frame to another frame, always going to be the same time interval. All right. So, and if the change in position is also the same, that means this is, let's say, delta x1, which is the change in position between, x2 minus x1. That's the change in position. Or delta x2, which is x3 minus x2. That means this distance, for example. If they're all the same, delta x1 is equal to delta x2, and so on and so forth, then one thing we can say here is that this object is in basically moving with constant speed. Okay, so it's moving in constant speed, and we have another name for that. We call this a uniform motion. So this is a uniform motion. Again, what is uniform motion? Object moving in a straight line with constant speed. All right, and the speed generally is defined as distance over time. So basically how much distance, right, it covered during this time interval, right? And that distance over time gives you the speed. So if I calculate the speed for this first time interval, and then the speed during the second one, and the speed during the third one, I'm going to get the same thing, because all of those three have exactly same distance and exactly same time interval. So I'm going to get exactly same speed for all of them. So that's why we can say it's a constant speed. Constant means it's not changing as a function of time. All right, so, but obviously one of the things we can also have is, sorry about this, picture that should not have been there. For example, I have here is a person, right, an object, in this case a sprinter, moving as a function of time. So what I do here is I take this to be x1, then this to be x2, this to be x3, and this to be x4. And remember, again, time interval is still exactly the same. Let's say, take it 1 second time interval. One thing you can see here is this. This is the distance from x1 to x2. This is the distance from x2 to x3. And this is the distance from x3 to x4. That means there is an increasing distance, right, as a function of time. That means going from one frame to another, or from one time interval to another, the distances are increasing. So that's why if I look at sort of like, let's say, a speed, for speed 1, which is basically, distance, let's say distance 1 over time, I'm going to get a different number than I calculate, for example, speed 2, which will be distance 2 over time. Why? Because distance 2, right? So this much distance is, greater than this distance. And the third one is going to be even, longer distance. So that means the speed going to be increasing. So this is what we call object, in the process of speeding up. So it's increasing its speed, it's speeding up. All right, so that means if the object's speeding up, that means the speed increases and the distance between time intervals also increases. But here's another example. For let's say this is x1, this is x2, this is x3, and this is x4. In this case, again, 0, 1, 2, 3, we can see that opposite happening. That means, if I'm looking at distance 1, let's say it's greater than distance 2, right? And greater than distance 3, and so on and so forth, because that means what we have is there's a decreasing distance, which means that object is slowing down, right? So object is slowing down means that, distance will be decreasing, which means also the speed will be decreasing, right? So slowing down means that distance will be shorter and shorter for that time interval, means that object is moving slower. That's why it's covering less distance. All right. So obviously, example, car stopping for a red light, right? So this example is not something we're going to be looking at in this chapter, not even next chapter. This is actually jumping ahead a little bit. This is chapter 3. This one represents a little more complex two-dimensional motion, because if I take then sort of like the object here, look at that. So now I have two coordinate system, x and y. So then as a function of time, I can see that object here, let's say if this is x1, this is x2. But there's also, a y1 and there's y2. Then object is here. x3. So technically I can look at it as just horizontal motion, right? x1, x2, x3. But because it also changes the vertical position, which it didn't before, right? I have to also take that into account. So that's right, and so on and so forth. So we have to kind of look at in terms of both of the dimensions, So jump shot from center court. And in this case, you can see, right, ball is slowing down as it rises and speeds up as it falls. So one of the things we can see is that if I'm looking at, in terms of the x4, x5, x6, in a way you can see in a horizontal direction, nothing happens. But in a vertical direction, you can see, right, y1 to y2 is larger than y2 to y3, and even smaller than you get from y3 to y4. But then when it's going down, right, it's increasing speed. We're going to talk about that. This is basically a two-dimensional free fall. Because of gravity, right, object slows down as it's going up and then speeds up when it's going down. All right, so generally in my lecture notes, I'm going to have a lot of, these quick checks, which basically I'm going to show you sort of like, let's say, what I expect from a quick check, but most of the quick checks, I'm going to then leave it, for you to try on your own. But for example, here we have a motion diagram that are made up of two cars. Both have the same time interval between the photos. That means exactly same 1 second time interval. Which car, A or B, is going slower? So kind of, you look at it, you try to then use and apply the, the tools that you learned, right? Concept that you learned into, solving this problem. And one of the things you can see here is one car is moving to the right, the other one is to the left. Well, it doesn't really matter for us, right? I mean, if you're talking about in terms of which one is moving faster or which one is going slower, we don't really care, if it's going to the right or to the left, okay? So all we care about here is this. Remember, so we still have this, right? In terms of the time interval, that means this is, again, in terms of, time interval between them exactly the same. We are told that, right? But if I look at car A, I get this as a, let's say, distance between the time intervals. And one thing I can see here is that the car A, hopefully you will recognize, is moving at constant speed because the distance 1, 2, 3 are all the same. Time intervals are the same, so it's going to be the same speed. But if I'm looking at, let's say, distance here, right? Let me call it just D1. And here, let's say D2, it's going to be different than if I look at distance 1 prime, let me do it like that, for the car B. Since D1 prime is larger than D1, with D1 prime being car B, D1 is car A, then I can technically say that speed prime for car B will be greater than speed for the car A. That means the answer will be here is car B moving faster because during that 1 second time interval, it covers more distance, right? So, and generally the next slide will give you the right answer. So you have to kind of like think about it, choose the, one of the options and then verify that with the next slide. All right, so often motion of object as a whole is not influenced by details of the object size and shape. All right, so this is like really simplifying the problems, really simplifying the motion, but it is necessary for, let's say, for this particular chapter because we're just learning about motion, and it's important for us to simplify things. And it's nothing wrong with starting with, simple, let's say description of the motion, and then add more layers and more layers as we go and learn more and more. Okay, so right now we're doing this. We're assuming that size of the object and shape of the object, not important. That means what we can do here is, as object is moving from point A to point B, it could be, let's say, a bowling ball, it could be a ping pong ball, it could be a car or an elephant. For us, we don't care. And as long as they're moving, let's say, the same speed, they're going to go from A to B exactly same, let's say, time, right? And what we have here is we're going to see that this is, works actually really well. So we only need to keep track of a single point on the object. okay? That means we don't even care, not only like, let's say size, but also shape. So we can treat the object as if all its mass were concentrated into a single point. We're going to see, right? We're going to can call that later on a center of mass. But then that mass at the single point in space is called then a particle. So this is what we do in physics. A lot of times we, use like, let's say, a simple model to describe some kind of phenomena. All right, so particles have no size, no shape, and no top, bottom, front, or back. That means one of the things we can do here is we can represent any object that we consider a particle with just a dot, okay? Because it doesn't, doesn't have a size or shape or anything like that. So that means we can, that's why it's a particle, right? We can represent it as a, with just a point particle, sometimes it's known. That means the car that we had in previous slide, for example, I can represent it with a dot or a point. A person with a point, an elephant with a point, anything that we want, as long as we don't really care about its size or shape, and we're not going to be caring about its size or shape, at least until chapter 4. We can then just simply represent everything as a particle. Okay, that means this is our object at initial time, and let's say this is our object at 1 second later, 2 seconds later, 3 seconds later, 4 seconds later, and things like that. What I can do, I can draw a coordinate system, and I can then put them here in terms of, all right, so this is x1, this is x2, x3, x4, and so on and so forth. Or I can, follow this, x0 can be like, let's say, your initial position. Sometimes that we do that in physics, like x0, or sometimes like we call it x naught, is the position initial time. In our book, we also use x sub I to represent that, which is initial position, I for initial. That means, generally what we want to know here is, let's say it goes from 0 to 1, okay? Then this will be then, let's say, final position. And what we want to know here is, let's say we're given the time interval. Time equals 0, time equals 1 second. Maybe we want to know what is actual distance, what is delta x, which will be then x final minus x initial. Okay, so we're going to see that this is actually known as a displacement, change in position. All right, so motion diagram then can be simplified into using the particle instead of an object. Obviously, we started with a person running, we use that person as in the picture, or a car. But imagine, right, on the exam or something like that, it's so difficult to write, or draw all those, cars and pictures of the person and all those things. And much simpler to just represent a dot, a point, right? So what we have here is, you can see, right? So the numbers show the order in which the frames were exposed. That means basically the time, right? 0, 1, 2, 3, 4. And what we have here is, so let's say this is now vertical. I can draw a vertical line. I can take this to be the origin, right? And then, what I have here is, let's say this is position 0. Then this will be position 1, position 2, position 3, position 4, and so on and so forth. Okay. And this is basically motion diagram of a rocket launch. Because, one thing you can see here is going from the first, let's say, distance from 0 to 1, and then the second one, and then the third one, we can see that distance starts increasing over time. That means this is the object which is, speeding up as a function of time. And that's what the rocket has to do, right? Rocket has to speed up in order to escape Earth's gravitational pull. All right, so here's one more example in terms of a quick check. Again, I'm doing this, in this chapter, I'm going to do a couple of those, but then, generally I'm going to expect you guys to do the rest of them. All right, so we have 3 motion diagrams as shown, which is a dust particle settling to the floor at a constant speed, which is a ball dropped from the roof of a building, and which is a descending rocket slowing to make a soft landing on Mars. Okay, so now what we have here is we have 3 options, right? So we have A, we have B, and we have C. And we want to look at them and understand what's going on. So if I look at A, I can then take this to be the initial position. okay? And I can see that as the time goes, object increasing the, the distance, right? Increasing the distance traveled, which means that this is object speeding up. And what we have here is if you drop a ball from a roof of a building, it will be speeding up as it's going down. And again, the way I know here is the distance here is less than the distance after, 1 second later, let's say. That means every, additional second gives us a longer, a distance that was covered. All right, so let's look at B. For B, we have, this is distance 1, this is distance 2, this is distance 3, right? And you can see, right, they're all exactly the same distance because the distance between all of those dots is exactly the same, which means that there is no change in speed because speed is the, remember, so speed, generally we use V for speed. So let's say V1 equals D1 over T, or like delta T. And you can see, right, since D1 is same as D2, same as D3, they're all going to be the same. So V1 is going to be equals to V2 and so on and so forth. And this is going to be, a dust particle settling on a floor at constant speed. The last one is then, here's the distance D1, right, during the first time interval. But then here's D2, D3, that means as a function of time, distance starts decreasing as you're going down, which means that you are slowing down. And that's what we have, descending rocket slowing to make a soft landing. That means what we have here is so for the dust, which should be the first one, so the dust is B, then the ball here is dropping is A, and then the rocket is C. That means our option will be B, A, C. And then you look at which one here is. So A is dust. No, because what we have here is A is basically the ball, right? So we look at, so that means we can eliminate this, and we can eliminate that, we can eliminate this. So then we have A here is ball, A is ball. That's what we have. B though, so let's say B was the, here, B here is the dust particle. That means if I come back, this is rocket, so I eliminate this, and then I have this as the right one, and then the C here is the rocket. That means B here is the right answer because, I need to understand first what each one of them represents, what type of motion, so then I can go ahead and answer the question. All right, so here's some other, conceptual, examples. So let's say a car skids to a halt to avoid hitting an object in the road. Okay, that means a car is moving and then is basically, it says it skids to a halt. That means it is slowing down. To a halt means it stops. That means it is slowing down until it stops. It says draw a basic motion diagram using images from the movie from the time the skids begins until the car stops. So for example, here we have an example of, visually cars, right? You're drawing the cars. You can see that here's, let's say, X0, X1, X2, X3, and X4. And you can see then what you have here is this represented with D1. This is D2, and so on and so forth. This is D3, and this is D4. What I have here is, remember, then 0, 1, 2, 3, 4. Those are the time intervals. So if I'm looking at this D1, D1 represents then velocity during that time interval, or the speed. So I can look at it in V0, which is then D1 over delta T1. But remember, delta T1 is equals to delta T2 is equals to delta T3. This is the time interval between the frames. They're all exactly the same. That means what I can see here is that I can use the V0, right? And that will be D1 over T1. V1 will be then D2 over delta T2. V2 is D3 over delta T3, and so on and so forth. Now, what I can do here is we're going to learn later on that these are vectors. velocity, is a vector. Speed and velocity. Speed is the magnitude of the vector of the velocity. Speed just represents how fast it's moving, but velocity is actually a quantity that represents not only how fast something is moving, but also in which direction. So then we can also represent that with an arrow connecting the position 1 and position 2, let's say in this case. So going from the initial position to the point 1, right? We drew an arrow which represents the magnitude of the velocity, which is how fast it's moving, and also in which direction. That means we can use that additionally to the motion diagram to represent, object's motion. Because think like this, if you look at then those arrows, you can see, right, V1 is a longer arrow than V0 is longer than V1, V1 is longer than V2, V2 is longer than V1, which means that speed is decreasing as the object moves in the same direction. That means it is slowing down as it's moving to the right. Okay, then this will be pretty much the answer to this example in terms of doing the doing the motion diagram. And we will learn how to do motion diagram in terms of just dots, right? But now what we can do here is we can connect those dots with an arrow, and that's basically is the velocity. So this is V0, V1, V2, V3, but because it's a vector, we put an arrow on top of the V, just representing that this is a vector. That arrow doesn't have a direction. So like, let's say, for example, if the object is moving to the left, then I don't just take the velocity and move the arrow on top to the left. No, this is just a notation. That means the arrow above the velocity is always pointing to the right. That's how we represent the, a vector notation. All right, so here's another one. This is another useful tool that we're going to be using. And this tool represents, let's say, a motion. In this case, you can see, right, it's a two-dimensional motion. And this motion is, again, actually, let's say, it is a motion diagram, but it is, plotted in terms of y-axis and x-axis because, let's say, as we learned, right, in a two-dimensional motion, what we have here is the object here is then covering both horizontal distance and vertical distance exactly the same time. All right, so then we use the motion diagram, and what we have here is you have horizontal position. So basically we have a Cartesian coordinates and a vertical position. We have then, we show in which direction the x is increasing, becomes positive, in which direction it is negative, which means, like, let's say then what we have here is, then let's say this to the left will be negative position for the x, and then down will be then negative position for the y. Okay, and one thing we have here is then in terms of, let's say, -3, -6, -9, we are basically using those as to represent position. Okay, so for example, see at 0.5 second, at 0.5 second, the object's horizontal position is then has to be written as x, let's say x1 here is plus 3 meters. So indicates that it's not 3 meters to the left of the origin, because origin then becomes our reference point. Okay, that means our Cartesian coordinates always take the origin as a reference point, and then the position of the object is given either in terms of positive or negative, indicating if it's to the left or to the right of the our reference point. Same way, right now I can write y1 to be plus 6 meters, to make sure that we understand it's above the origin rather than below the origin. Because what I have here is when I talk about let's say half a second later the object covered 3 meters distance in the x direction, well, maybe it's moving in this direction. Nothing wrong with it moving in this direction, right? So I have to indicate, let's say, what is the position 0.5 second later, if it's to the right or to the left of the origin. So that's why at least in the beginning, right, try to always put the positive in front of the position or whatever, let's say, while you're writing, because that plus or minus in physics generally indicate a direction. So let's say when I put x1 equals plus 3 meters, this means specific direction in terms of this is the position change to the right rather than position change to the left, if I'm talking about, for example, in the x direction. Same way up or down for the y direction. All right, so I'm kind of do this. Okay, so then what we have is this. Shown is the motion diagram of a basketball with 0.5 second intervals between the frames. Okay, you can see, right? So this is a two-dimensional motion. You know, object covers basically position in both x and y directions as it's, you know, basically moving. So, and we have a coordinate system added to show the two-dimensional motion. Okay, so the frame at t equals 0 is frame 0, and when the ball here is at the origin. Generally, what we do is we can always assign the initial position of the object to be the origin because we have that freedom. Every time the object starts from somewhere, we can easily take that, you know, initial position to be the origin. Doesn't matter if it's moving to the right, to the left, up or down, we can always take the initial position of the object to be the origin. All right, so then what we have, for example, here is then the ball's position in frame 4 can be specified with the coordinate x4, y4, and then we can see if we measure, right, it's going to be then 12 meters to the right and 9 meters up, basically. That means position of the object, you know, let's say at t4 equals 2 seconds, right, is right here. That's the, you know, position of interest. Okay. Now, what we want to do here is then we want to find out, let's say, what is the position vector. Remember, now what we have here is we have generally two quantities that, you know, we work in physics with. That two quantities are vectors and scalars. So here is vector and scalar. All right, so a scalar is the easiest one because it's a quantity that represents some kind of, you know, something that can be represented with just a number. For example, object's mass. When you say, you know, something is 10 kilograms, there is no some kind of direction attached, right? So that means the scalar is directionless quantity described with some number and a unit. Mass, temperature, distance, speed, those are all scalar quantities. So mass, distance, you can see, right? Speed, those are all can be described with just a number and a unit. So when you say, let's say I'm driving 20 miles an hour, you're just saying how fast you're moving without necessarily giving me any information about in which direction. But vector quantities require direction. So then, for example, when you want to move from point A to point B, you want to know how far that point B is from point A, and also in which direction should you move to get to point B, right? So let's say if I tell you move 20 meters, well, you can move 20 meters in every single direction, right? So 360 degree, move 20 meters. So, but when I tell you move 20 meters to the left, then I'm giving you basically very specific distance and direction. So that basically a vector, because I'm giving you not only how far to move, also in which direction. So that's kind of what we're going to be doing. And vector quantities are going to be used a lot. Okay, so we're going to be spending a lot of time learning about vectors because, for example, velocity, acceleration, force, displacement, and so on and so forth. They're all vectors. That means they're all directional, and we have to then use certain approach dealing with those type of quantities. All right, so we start with the position vector. Okay, so let's say, remember, we assume that frame 4 is our frame of interest, and then we represented this position as x4, y4, right? And we found, let's say, that it was 12 meters, let's say, in this direction, right? And it was, I think, 9 meters in this direction. So let's say 12 meters and 9 meters in this direction, okay? And that means technically what we have here is that delta x, which is change in x, was 12 meters, and delta y, change in y, was 9 meters, okay? But one of the things I can do here is I can then look at directly going from our origin, the starting point, to that frame 4, okay? And what I do here in this case, I represent this, distance and direction from the origin to the frame 4 directly, right, to that position with an arrow. Okay, so this is known as a position vector R. So this is, let's say, R. And this is for frame 4, so this is R4. So for example, this will be then R1, right, for the frame 1. Remember, R is a general distance, and arrow on top means that it's a vector, which means that this vector R must have two things. It must have a magnitude, which means basically its size, and it must have a direction. Okay, so now one thing we can talk about here is first, let's say, magnitude. How do we find the magnitude? Which basically the size of this particular distance, right? Or that, how much distance that vector represents. Well, one thing we know, hopefully at this point, is that this is nothing but pretty much Pythagorean theorem, right? So you have this as 9 meters, this is as 12 meters, and if I have a triangle like this, where this is 12, this is 9, then this one here is square root of 12 square plus 9 square, right? So then I can calculate this to be 15 meters. That's why we get that 15 meters as its size, okay? That means we can find that size of that position vector R4 as 15 meters. Now, how do we represent then direction? Well, one of the things we learned from the Pythagorean theorem here is we can also find the angle theta, right, of that hypotenuse relative to the adjacent and opposite sides, which means we can use tangent of theta, which will be then 9 over 12, and then finding the theta from that inverse tangent, right, we can then find this to be 37 degrees. And that's how we get that 37. Because if I'm considering position vector, it has to have two things, right? So magnitude, direction, because any vector comes with those two components. It has to have a size and it has to have a direction, right? So that's kind of what we have. That means this is pretty much using polar coordinates. So every time we're dealing with vectors, we will be using basically a combination of Cartesian and polar coordinates. Okay. All right, so then one of the things we have here is if you have then, let's say, more than one vector, you can actually even add vectors together, okay? So you can add vectors together and, for example, or you can subtract vectors, from one another and things like that, okay? So, and in this particular case, it gives you how to add two vectors. And let's, generalize and say that, we're using some vector A. It can be anything. It can be displacement, velocity, acceleration, some kind of quantity that has a size and direction. So let's say this is that vector A. Again, what we're doing here is any vector can be represented with its, with an arrow, right? So the length of the arrow is information about magnitude, and then you have the direction. So this is technically then one of the ways to add vectors. This is a graphical way of adding vectors. So we're learning how to add vectors graphically. So let's say you have two vectors. Here's vector A and here's vector B. Okay. So if I want to then add those two vectors together, add vectors A and B together, then I can use sorry, what we call tip to tail method. So tip to tail method. So this is a graphical method, tip to tail, which means that you take vector A, okay, then you move vector B such that it basically, the tail of B connected to the tip of A. So then you have this. So this is then vector B. So that's why tip to tail, right? Tip to tail. And then what you do here is the resultant vector. That means, you know, when you're adding A plus B, you're technically getting another vector. Let's call this resultant R vector. So then this vector will be a vector that always going to start from the very initial point. Let's say this is initial point to your final point. That means the tail of A to the tip of B. And this will be your vector A, vector R in this case, which is the resultant. When you add those two vectors together, you're basically getting a third vector, which has a magnitude and direction, right? Its magnitude, since let's say here A and B are perpendicular to one another, then what I can do here is I can take vector A and let's say I can say, all right, so here's the magnitude of vector A. I can just write it A without an arrow. That's its magnitude. And then let's say this is the direction of A, and here's vector B. This is its magnitude, and this is its direction. Then magnitude of R, in this particular case, because they're perpendicular, will be just given A squared plus B squared. That means the magnitude of A squared plus magnitude of B squared, then take the square of that. And then we can find that direction again using the Pythagorean theorem. Yeah. So this is then vector addition. And, you know, technically this would have been also correct if the A and B were not perpendicular. So for example, in this particular example that I have on this slide is they're not, you know, perpendicular, right? So let's see what we have. So Sam is standing 50 feet east of the corner of 12th Street and Vine. He then walks northeast for 100 feet to a second point. What is Sam's changing position? All right, so let's see what we have. So one of the things you want to also understand is that when we use coordinate systems, sometimes also use this, you know, west, east, north, south coordinate system as well. Okay, that means we will use, you know, north, south, east, and things like that. So let's say in this case, it says Sam is standing 50 feet east of the corner. That means this is taken to be the origin, right? The corner. You are 50 feet east of that. Since this is our east, right? So then we can say that this is the starting position. And relative to the origin, this is that position vector. Okay, so this is the position vector. Let's say in this particular case, your starting point, we don't take that as a reference, but we find its position relative to the origin. Okay, so that's why we can say then R0, right, or R naught as a, you know, position vector is equals to 50 feet, and we can put like east as the direction in this particular case. We can say it's just east. Because, you know, if I say that 50 feet east, you know in which direction that vector is pointing, right? Then it says, he then walks northeast for 100 feet. All right, so northeast means north of east. That means from east, you move toward north. When you're not given any type of angle, let's say 20-degree northeast or 30-degree northeast, and it says just northeast, it means that it's 45 degrees, you know, with respect to east toward north. Okay, that means this is then this direction, right, is 45 degree with respect to north from east, kind of like you can think like that. All right, that means, you know, we come to this position over here. All right, so we come here over here, and this is our final position. Now let's look at then what we have. So we have then this particular vector, first vector R naught. And now we have this vector here, delta R. And what we get here is this. So this is our starting point, right? And this is our end point. So if I look at the position of the end point relative to the origin, then R1 as a vector, right? So this is that R1. This is the position vector for the, this end point, okay? And this is the position vector for the starting point, okay? All right, so then technically what we have, delta R represents change in position, right? Because we went from this starting point to this end point. And this vector is the delta R, change in position. Now, we just learned that if you're doing tip to tail, then one of the things you can do here is this. Take your first vector, R naught, then add it to a second vector, and the second vector connected, the tail of the second vector connected to the tip of the first vector. That means delta R is connected to the, R naught vector. So that means we have R naught, and then we have delta R. And then when I connect the tail, from the tail of R naught to the tip of delta R, then this is our R1 vector. Okay. That means R1 is basically our resultant if I add those two together. It means this is equals to R1 vector. So then what I have here is this. See, if I rearrange this to solve for delta R, then what I'm getting here is this. Delta R is equals to R1 minus R naught. Okay. And this then delta R vector here is known as the displacement of the object, okay, which is change in position. Because what we get here is we have a position, starting position, which has its own vector position. We have end position, which we have R1 as its own position vector. But then delta R represents change in position going from the starting point to the end point. And we find this delta R, right? So we find this delta R by subtracting R1 and R initial. That means basically final minus initial. That's kind of how it works. That means displacement vector is nothing but the difference between initial position, final position vector, and initial position vector. So that's kind of what we have. So displacement delta R of an object as it moves from its initial position, R initial, to the final position, R final, is given as delta R. So that means in a way what this delta R represents here is you have a change in horizontal position. You can write it in terms of delta X, which will be X final minus X initial if you're changing your position only in the horizontal direction. Or you can also look at it in terms of if there's a vertical change in position as well. So then you can have only that. Or you can have both, right? Or you can have both, like in the previous example, because if you start from here and move over there, you change your position in the X direction and in the Y direction. So that, and this being, let's say, your delta R. Okay. So the definition of delta R involves vector subtraction. Now there are some things we can talk about in terms of vectors. See, let's say this is a vector B. See, if I have the same magnitude vector but in opposite direction, then it's basically same vector B but negative of B. So I can say that this is just negative of B. And if I'm adding those two vectors together, vector B plus negative of vector B, I'm going to get a vector with zero magnitude. So I get basically zero. So this is usually what you have when you subtract vectors. So with numbers, subtraction is the same as the addition of a negative number. So similarly, A minus B, we can just write this as A plus negative B, right? Because, when you're adding them together, when you're subtracting, right, it's basically the same as adding a negative of that, vector. So that means A minus B can just basically written as A plus of negative of B. And here's an example how to do the vector subtraction. So let's say here, remember, resultant vector is equals to, now instead of A plus B, it's A minus B. And these are the two vectors we have. We're going to be using the same two vectors. And I'm going to be using, again, tip to tail. But remember, tip to tail works when you're adding vectors. That means what I do is I rearrange this. I say a plus the negative of b. That means I need to first find the negative of b and add negative of b to the vector a. Well, negative of b here is this vector. Same magnitude, but opposite direction. This is negative of b. So then when I take vector a, I'm adding to vector a a negative of b, which means this is the negative of b. And then I do the tip to tail. This is then the resultant vector. Okay. So this is r minus b, technically. So I just wrote it as a plus negative of b, but technically this is equivalent to a minus b. Okay. So that's kind of what we end up. And that's what the resultant r is, just a difference between them. Okay. That's pretty much what it shows over here. All right. So here we have P and Q, and we're adding P plus Q. What will be then the resultant vector? All right, so now what I'm going to do here is I'm going to show you that there are two methods that we have. And the first one I talked about already, which is the tip to tail method. The other one is parallelogram method. So let me show you then parallelogram method. I imagine right now you can do the tip to tail method on your own, but this one here is parallelogram. All right, which means in this case, instead of moving something like this, tail of the second one, say P is the first one, you leave it alone, and then you move the second one. But second one now, instead of moving this here, like we did for the tip to tail, you take it and move it over there. That means you connect the tails. That means what we do here is we connect the tails. And here's then this vector Q. Tail of Q connected to the tail of P. Right? Then what we do here is we construct a parallelogram. That means something like this, which is kind of like projection of P and then projection of Q. And then the resultant vector goes from the, where they're connected at their tails, right? And diagonally like this. This is then the resultant vector, P plus Q. Okay. And if you're looking at it in terms of which option, obviously not this, not this, not that. So it has to be, you know, the first one. Okay. And there you go. That's what we have. So again, remember, I use the parallelogram method here. And then here's the tip to tail method. And you will see it's exactly the same thing. So it doesn't matter if you use parallelogram or the tip to tail, you're going to get the same thing. The only difference here is that when you're using parallelogram method, you're dealing with only two vectors. But when you're using tip to tail, you can say, all right, so here's one vector plus another one, plus third one, plus fourth one, plus fifth one, plus sixth one, plus seventh one, right? And then this is where you stop, this is where you started, and this is the resultant. That means you can actually work with many, let's say vectors together, if you, using tip to tail. But the parallelogram method is always two at a time. That's kind of like a restriction for that. All right, so P minus Q, which means you find the negative of Q, which is here. And you say it's P plus negative of Q. So that means you put the negative of Q right here. And then construct a parallelogram. And that's our resultant vector, which is this guy over here. All right. Again, this one here is you can use then the tip to tail method to get the same result. All right, so now one of the things we're going to be doing here, we're going to be learning some definitions and things like that of the things that I already mentioned. So you can see, right? So let's say it's useful to consider a change in time. All right, so that means, we're using delta t, which means that, t final minus t initial. That means if you have a time interval, right, going from initial position to final position, then you can look at in terms of delta t. All right, so generally position at t initial is r initial, and then the position at the t final is usually given as r final. That means, for example, if object is here at t equals 0, t initial, right? So we can say that this is basically x initial, and it goes to this position at t final, then we can say that this is x final. Why am I using x instead of r? Because I'm using one dimensional. So I'm going to use one dimensional in this chapter mostly, and then also the next chapter. That means my displacement vector is this guy over here. This is my displacement vector, and it's delta x instead of delta r. Why? Because it's only horizontal change in position. All right, so then what I have here is if I'm calculating just how fast the object is moving, then I can look at in terms of the speed. So let's say the object goes from this position to that position, right? X initial to X final. Then what I can do here is this. I can calculate object's fastness or slowness in terms of the distance traveled, not the displacement, but distance divided by the time interval. That means d divided by delta t. So this is known as the average speed. When you're doing the ratio, it's average speed. Average speed does not include information about direction because speed is a scalar. Remember, right? It's a scalar quantity. What I need here is, if I want to include the direction, I have to look at average velocity. And average velocity is then going to be the displacement over time. And since the displacement is a vector divided by the time, so then your velocity is also a vector. And this ratio technically gives you average velocity, okay? Average velocity, because for example, if you are going from this point 1 to point 2, and let's say this is, I don't know, 100 miles, right? You can imagine, maybe sometimes you're moving faster, sometimes you're moving slower, right? 100 miles, you can, hardly always make, drive at the same speed. Sometimes you move faster, slower, and things like that. So this is then the average. What is the average velocity and average direction as you moved from point 1 to point 2? All right, so let's kind of then look at in terms of, units. So here delta r is the distance or displacement, right? I mean, it's a position change. And generally given in terms of meters or miles or, I don't know, centimeters or feet and things like that. But let's say we're going to see in a little bit, that the system that we're going to be using, right, to indicate the distance and things like that generally is in terms of the SI unit, which is one specific type of unit that we're using. And that's going to be basically in terms of the meters. So the unit that we're going to be using to describe the position change is going to be in meters, because we want to be consistent in terms of, let's say, one specific type of unit that we're using. As I said, right, you can say, inches or feet or miles or, meters, or kilometers or centimeters. Let's instead of all of that, agree to one specific unit and then always use that. And that one specific unit is basically meters. And then this is then divided by time interval, which is generally in seconds. So then velocity or speed, then always going to be in terms of meters per second. And that's what I usually use. In this class, I always use meters per second. All right. So then velocity vector is in the same direction as the displacement. Because if you start from this point 1 and you go to point 2, right? So I can say that this is my displacement vector. But velocity is that, you're also moving from point 1 to point 2, right? That means if I'm doing the velocity as a vector, it's also going to be in the same direction. So this will be my delta x as a vector, and this will be my velocity as a vector. Let's say average velocity. Okay, that means they're going to be in the same direction. So the length of v is directly proportional to the length of delta r. Why? Because v average is equals to delta r over delta t, right? You can see, right, directly proportional. Consequently, we may label the vectors connecting the dots in the motion diagram as a velocity. So that's why this is position 1, 2, 3, 4, right? So let's say x1, x2, x3, x4. I can then, the distance between those positions, I can use that, the vector representing velocity rather than displacement, because it's easier to look at the velocity vector to understand the motion. Because look at this. This is velocity going from x1 to x2. Velocity from x1, x2 to x3. Velocity from x3 to x4. Now, what we see here is all of those three velocities have the same direction and have the same magnitude, which means they are equal to one another, which means this is a constant motion, right? Or remember, constant motion we define as uniform motion, which means it's constant velocity, not constant speed, but constant velocity, because we're not only moving at constant speed, but also same direction. Now, remember the vector. So let's say if I'm doing velocity vector, vector should have a magnitude and direction. Now, the magnitude of the velocity vector is nothing but the speed of the object. And then let's say we have a direction. That means the speed is magnitude of the velocity as a vector. Okay. So then if I comparing to the other, tortoise, let's say this was a hare, this was a tortoise. One of the things we can see is that, all right, so here's the velocity 0, velocity 1, velocity 2. Well, it's also a uniform motion. Why is it a uniform motion? Because same velocity for those 3 time intervals. Constant velocity. Okay, so then what is the difference between hare and tortoise? Well, the constant velocity for the, hare is just basically longer as a vector, which means that, larger magnitude. That means overall faster moving, object, right? That's kind of what we can think of, like, let's say, because this arrow is longer than that arrow means, higher magnitude, which means faster speed. All right, so here's another example. Softball player hits the ball and starts running toward first base. Right, so they use the particle model to draw motion diagram showing her position and her average velocity vectors during the first few seconds of the run. Right. That means we take the softball player as an object, and as an object, we don't care about size or shape. So all we have to do here is represent her as a particle. Okay. And one of the things we have here is that she starts running toward the base, right? She hits and starts running. That means what we have here is, here's the starting point. And then let's say she starts running. Obviously she starts from rest, and then she's going to start running, and she's going to go faster and faster. That means she's going to be covering more and more distance as a function of time. So then if I'm doing the vector, a velocity vector, I'm going to be getting something like this, which means, increase in speed, increase in velocity, right? So basically something like that, right? So that means object, object in this case, the softball player is speeding up as she's moving, let's say toward the base, okay? And direction was technically, arbitrary, right? The trivial, I could have chosen to the left. I could, I just chose to the right, just a standard. But, in this case, nothing would have been, wrong if you chosen the, her to be moving to the left. Right. So what if the object, for example, right? So we talk about the softball player. One of the things we see here is, so actually, let's go back for a second here. So let's say this is V0, V1, V2, V3, V4, right? V5. That means what we have is increasing velocity. That means I can look at V1 minus V0 over delta T, or V2 minus V1 over delta T. Remember, the time intervals are the same. But then one of the things we can see is that, this ratio, right? V3 minus V2 over delta T, we're going to get non-zero, ratio, because V1 and V0 are not the same. V2 and V1 are not the same, right? So this is longer than that. This one is longer than that. So if, for example, I have V2 minus V1 over delta t, but V2 and V1 are the same, which means that it's a uniform constant velocity, then I'm going to get a 0, which means there is no change in velocity. Velocity is constant. But in this case, my delta V over delta t is not equals to 0 because my velocity is changing, increasing. So what we do here is then we talk about that. So when the velocity, object velocity basically changes as a function of time. Remember, so sometimes the object's velocity is constant as it moves. When it's constant, then delta V is 0. There is no change in velocity. But when the object is actually changing velocity, either increasing velocity or decreasing velocity, right? Either way, what you get here, then this ratio here is non-zero. And that ratio is then defined to be the object's acceleration or average acceleration if you're using this ratio. So then what we have here, then this is the object's acceleration, which defined as changing velocity as a function of time, okay? So object changes velocity by speeding up or slowing down, or one of the things we're going to see later on, object can also change the velocity by changing direction. Because remember, velocity is a vector, and vector has magnitude and direction. You change magnitude, you're changing vector. You change the direction, you're changing the vector. Okay, and that means the average acceleration is defined as changing velocity, either in terms of magnitude or in terms of direction, or maybe even both. All right. So this is kind of what we have. Think like this. So Vn is the initial velocity. Vn plus 1 is the, a velocity at some later time. So then you can see, right, then delta V here is, the final velocity minus initial velocity. So Vn plus 1 minus Vn. So that means if I'm looking at this, acceleration basically represents this change in velocity. It's proportional to this change in velocity. Okay, so this is my delta V. And then acceleration is proportional to this delta V as a vector. It's always going to be in the same direction as the delta V. Okay, it's always going to be in the same direction as delta V. So you can see, because, if I subtract those two together, I'm going to get this as delta V. So then I can say that's the direction of the acceleration, because acceleration is proportional to the change in velocity. And it's a, if you're talking about it as a vector, right? It also has the same direction as the change in velocity. All right. Now, acceleration is very important for us to understand the motion, because one of the things we have here is if the object is moving in some specific direction and you know about the acceleration in the system that is given to you, you can figure out if the object is going to be, speeding up or slowing down. Because, for example, then what we have is this. When an object is speeding up, the acceleration and velocity vectors point in the same direction. So here's that example. See, let's say you have an object that is moving to the right. So here's this object moving to the right. If you have acceleration that is also to the right, okay, then you know that the next velocity will be longer. Then, let's say, assuming that acceleration is constant, that means this acceleration as a vector doesn't change in terms of its magnitude and direction, then you can say that as long as acceleration is in the same direction as the velocity, you're going to speed up. Okay. Same thing, let's say if you're moving to the left and there's acceleration to the left, so this is velocity vector and this is acceleration vector, so you're going to be speeding up because acceleration and velocity in the same direction. But if you happen to have acceleration in the opposite direction, so for example, here's object's motion to the left, but then velocity as acceleration here's to the right, which means in the opposite direction, then what we do here is we can then see that object will be slowing down because of, let's say you have a negative velocity, and again, negative because it's moving to the left. So let's say negative velocity, but positive acceleration, and acceleration positive because it's pointing to the right. Remember, general coordinate system, to the right positive, to the left negative. Negative just means to the left, nothing, that's why I can sometimes say left, sometimes can say negative. Those are the same thing basically. So you can see, right? Velocity is to the left, acceleration to the right. That means they have opposite directions. Then the object is slowing down. That means that's the thing. Same direction vectors for velocity and acceleration, your system speeding up. Opposite direction, your system is slowing down. Okay. So let's look at then this quick check. So here's your initial velocity, and this is the acceleration. The question here is, what will be the next velocity? It means I have a velocity vector that I have to draw over here. What should I do? Should I make it longer? Should I make it same size as the initial one? Should I make it, shorter, right? What will happen to the object's motion? Object, let's say, going down. Well, you have to see that, what you have, right? So you have down for the velocity, but up for the acceleration. And they have the opposite directions, which means the object will slow down, which means the vector that I have to draw here should be, let's say V2, right? Should be shorter, okay? This means it's longer, doesn't work. This means there's nothing there, doesn't work. Those also don't work. So it has to be then this P over here, okay? Because what I have here is there's gonna be velocity there, still same direction, but, just a little bit shorter. Technically by how much shorter, but exactly that much, okay? Because that tells you by how much it will be changing. Right. Here's one more example. So the figure shows the first 3 points of a motion diagram. Is the object's average speed between points 1 and 2 greater than, less than, or equal to its average speed between points 0 and 1? All right, so let's see what we have. So you can see, right? So you are given the diagram. Okay, so you're given the diagram, and you are told that this is where we start, right? This is where we start, and this is where we end up. And what we get here is we are given acceleration, which means, think like this. If you start from rest, for example, let's see. All right. Let's say you start from rest. Rest means you have no velocity. Let's say your initial velocity is 0. When your initial velocity is 0, doesn't mean there's no acceleration. Doesn't mean the acceleration is 0. Because remember, acceleration is changing velocity. It will be V1 minus V0 divided by delta t. Now, what we have here is, if there is acceleration, that means there will be change in velocity even if you start from rest. Okay, so let's say you can see, right, there's a acceleration in this direction, which means that your velocity will be changing by that much in that direction, which means that 1 second later, you're gonna have a velocity by that much. And then as long as you're maintaining that acceleration, your velocity gonna be increasing by exactly the amount of acceleration, right? So it's this much, and then this much, and then this much, and so on and so forth. What we have here is then this. See, there's acceleration, so speeding up, acceleration, speeding up, acceleration, speeding up, acceleration, speeding up. That means all the way to this point, right, there is going to be increasing in velocity, object speeding up. But then at this point, acceleration is 0, which means, for example, I don't know, so like 1, 2, 3, 4, 5. So this is V5, and this is V6. Then what I have here is this, V6 minus V5 over delta t equals 0. Well, it can only be equals to 0, not because of delta t, but because V6 is equals to V5. That's why if I take their difference, you're going to get 0. Which means that this indicates that there is no acceleration after that point. So if there is no acceleration, then V6 is going to be V5. Same speed, same velocity as before. This means there is no acceleration again. It means that if I draw V7, it should be equals to V6. That means after that, it's just a constant velocity. That means as long as there's acceleration, you're going to be changing your velocity. But if the acceleration is zero, you're then going to be maintaining the velocity that you had when acceleration became zero. So you have to be a little bit careful about that part. All right, so then summarizing in terms of what we learned, which is if you have a coordinate system, horizontal coordinate system, anytime your position is to the right of the origin, position is written as positive. Your position to the left of the origin, position written as negative. If you're moving to the right, we take that to be a positive velocity. You're moving to the left, then we take that to be negative velocity. Again, negative velocity just means moving to the left. Negative, positive for a vector just means direction. So that's why, for example, when I say V, like let's say, how do I make that you know that this is horizontal? Well, I put a subscript, Vx. So when I say Vx as a vector equals 3 meters per second, well, this is 3 meters per second, how fast is moving. Now, in which direction is it moving? We know it's horizontal because I have an X as a subscript. But you will not know in which direction it's moving until I put, like, let's say, plus 3 meters per second. Well, if the velocity is positive, it's moving to the right. But if you have a Vx as negative 5 meters per second, that means this is something that's moving at 5 meters per second, but moving to the left. So that's kind of what you have. Negative is basically indicates in which direction object is moving. Same thing if the acceleration is pointing to the right, we take that as positive. Pointing to the left, we take that as negative. Again, same thing, right? Positive, negative, indicating the direction of that particular vector. You can see here is the same thing is in terms of the vertical axis. So you can say that up or down, right? Up is positive, down is negative. That's the kind of like the standard. And if your position is above the origin, then you take that to be positive. It's below the origin is negative. Moving up is positive. Moving down is negative, and so on and so forth. Same thing with the acceleration. Okay. So the sign of position, X or Y, tells us where an object is. Sign of velocity, Vx or Vy, tells us which direction the object is moving. The sign of acceleration, Ax or Ay, tells us which way the acceleration vector points, not whether the object is speeding up or slowing down. Okay, so remember, so for example, if I have an object moving with the initial velocity of 5 meters per second, see this is in the X direction, and I let's say put Vx not equals plus 5 meters per second, and I draw this vector here. Now let's say I have given acceleration as a vector as plus 2 meters per second square. By the way, that's the units for the acceleration, meter per second square, because velocity, meter per second, divided by time per second, so meter per second, or meter per second square. Now, the question here is this: how fast will the object be moving during the next time interval? I'll give you like a second to think about it. What will be the speed 1 second later? Well, remember, acceleration tells you by how much your velocity will change. So it will change by 2 meters per second each second, and in which direction? Which in a positive direction. So if your object already moving in a positive direction, its velocity will change by 2 meters per second each second. And because the signs match, it's going to speed up by that much. So the next velocity, V1, is again horizontal. And this will be then increased by 2 meters per second in the same direction. So it will be plus 7 meters per second. 1 second after that will be 9 meters per second, and so on and so forth. That means acceleration just tells you by how much your velocity will increase or decrease and in which basic direction. All right, so here's a motion diagram. And one of the things we're going to be doing here is, which we're going to be, doing a whole lot more in the next chapter. We can also take this and we can see that we can break this down into 3 kind of three parts, three segments. Here's one segment because for the first 3 minutes, because t is in minutes, so 0, 1, 2, 3, it's moving at one speed. The next 3 minutes, moving another speed, all the same, but another speed. And after that, another additional 3 minutes moving at much higher speed. Now, what we're gonna do here is we're gonna actually use the time and position as data. So this is time, this is position, this is in minutes, this is in meters. And we're gonna say, okay, so when this is 0, let's say 60 meters. When, 0, 0. When this is 1 minute, this is roughly 60 meters. When 2 seconds, maybe 120. When 3 minutes, maybe 180. So then we're gonna then plot this as position versus time in a graph. And I imagine you guys can know how to graph this, right? 0, 0 goes here. Once, like let's say 1, 2, 3, 4, 5, 6. And this is maybe like, let's say in terms of increments of, I don't know, maybe like, let's say 30, right? 30, 60, 90, 120, 150, 180, and things like that. So I will do 0, 0, then 1, 60, 2, 120, and then 3, 180. And I will graph this, find the slope. I'm gonna just show you in terms of this particular one, first 3 minutes. What I have here is I'm plotting horizontal position versus the time. And this is an abstract graph, right? This is position versus time graph. Okay, position versus time graph. It just tells you how the position changes as a function of time. Now, I plot that, and one thing I can do a trend line. Now, remember, what I can do right now is this. I can find the slope of this line. And let's see what the slope is. Remember, slope is rise over run. Okay, so if I take rise over run, that means let's say I choose 2 points. Here's point 1, here's point 2, doesn't matter, right? Any 2 points. Point 1, point 2. What I do here is then I find, so this is a rise and this is run. And I do rise over run. So slope is equals to rise over run. All right, so but what is rise? Well, rise represents this vertical, change in position, right? That means rise is nothing but delta x. Well, then divided by run. What is run? Well, run is this, which is changing time. It means delta t. That means if I'm calculating the slope, I'm calculating this ratio of delta x over delta t. Do you remember what we learned about what this ratio is? Well, this ratio is nothing but V average. That means if you have position versus time graph, and you're finding the slope of that graph, that line, that basically gives you the velocity, which is average velocity during that 3-minute time interval. What is the average velocity of the object during that time interval? And one of the things we have is this. If you plot this and you get a line like this, which is a straight line, then this is indication that it's a uniform motion. And again, what is a uniform motion? It's a constant velocity motion. Okay, it's a constant velocity. That means one thing we have here is it's a tool, the graphical method, right? The graphing, position versus time graph, where you can use the data of the position and time to find the velocity by finding the slope of the position versus time graph. Okay. All right, so that's kind of, one of the things we have. Okay, so a motion diagram is one way to represent the student's motion, but then another way is to make a graph of X versus T for a student. And let's say we get something like this. Now, I only showed you for this particular segment, but then the second segment would have been this, and the third segment would have been that. Now, one of the things you can see here is this. If you plot them and find the velocity, this will be V1, which is the velocity during the first 3-minute time interval. This is V2, this is V3. What you see between them, the difference between them is that V1, V2, V3 have different steepness. So technically then, steepness also will give you a larger value, remember, right? If you're doing the graph, which means V1 is greater than V2, but then V3 will be greater than V1, which means that V1 gonna have a larger slope, which means it's gonna have a larger magnitude. And that actually agrees with this, right? So you can see, right, this is V3 and it's larger than V1, which means steeper your line, right? When you graph that, steeper it is, faster, the object moving during that particular time interval. So that's why the steepness is actually indication of how fast it's moving. And also, since the graph is above the T line, right? Above, let's say the T axis, right? That means this is an object moving to the right. If object was moving to the left, then that would have been, the same kind of like idea, but, below the T axis, because that's basically the object moving to the left rather than to the right. In any case, it's very useful, and we're going to be exploring that in greater detail in the next chapter. One of the things we have in the last part of this chapter here is in terms of how we can represent everything, let's say, when you're solving a problem, right? What are the tools, what are the things that we can use to help us solve those problems? Now you can see, right? Physics problems are often presented using words. The word problem, which, a lot of students hate word problems, but, those are the real life problems, right? So you have to actually learn those. You have to learn how to read a problem, identify the clues that are given, and, basically solve the problem. Think like it's a puzzle, right? You're given the pieces, you rearrange everything, you see what you're given, see what's missing, put them together and find the missing link. All right, so the part of problem solving involves using symbols and drawings to create a representation which is clear and precise. You already learned some things in this, in this chapter. So a verbal representation is a problem statement or restatement using words. One of the things we can do here, we can say that, okay, so this is what I'm given. I'm going to show you, let's say there's a table that we can always use. This is what we're given. This is what we need to find. We can also do a picture, like a rough picture using mostly, a particle model. You don't have to draw a car or a person, thing like that. You can actually use a particle. A graphical representation, which I just did for you guys, right? The student is moving, that motion can be, graphed in a position versus time graph. Also then at the end, sometimes you want to calculate things. And then, for example, we have learned few examples, few, formulas, mainly for the displacement, velocity, and acceleration. And then we can use those equations, right, to solve problems. So mathematical representation using specific equations and things like that. So that's how you approach. So you have all of those, let's say, techniques, right, methods that you can use to solve a problem. All right, so here's a simple problem. Again, most of the things in this chapter is simple, then we're going to moving to more problem solving starting next chapter. So your roommate drops a tennis ball from a 3rd-story balcony. It hits the sidewalk and bounces as high as the 2nd story. Draw a complete motion diagram of the ball from the time it is released until it reaches the maximum height of its bounce. All right, be sure to determine and show the acceleration at the lowest point. All right, so remember, when it says it's dropped, means it starts from rest. So you start from rest, and when you're dropping, you know that one thing is going to happen, it's going to speed up. So it's going to speed up all the way until it hits the ground. So now, you start from here. So let's say that in which direction will be the acceleration vector? Remember, in this case, you have 0 velocity. Well, remember, as soon as you drop, we know that it's going to be going down. If it's going down, that means its velocity will be increasing like this. And since you're increasing velocity, that means acceleration has to be in the same direction as velocity in order to increase the velocity, right? So that's why you're going to be increasing until you hit the floor. Well, in that case, what happens here is then it's going to bounce back. Bounce back means that you're going to have now velocity like this. Well, what you have here is generally there's a little bit of, like let's say friction and things like that. So this velocity technically going to be a little bit less than the final velocity over here. So there's a little bit of change, and that change is basically what the acceleration is at that instant when it hits the ground. There's acceleration which changes the direction of the velocity. But what I have here is when object is dropped, this acceleration is always due to Earth. And Earth always have an acceleration that it exerts on things that is always down. So that's why one thing we know is going to then slow down, slow down, slow down until it stops. And this is the second floor, right? So that means, this is going to be then, let's say, motion diagram for this particular motion, let's say. All right, so here's the picture again. Okay, so one thing we do in this last part is talk about those units that I mentioned. So we have three quantities that are, we call them fundamental quantities. And anything we learn in this class basically represented in terms of those three quantities. And those quantities are length, time, and mass. Those are known as fundamental units, fundamental quantities. That means every time you are presenting the length measurement or mass measurement or the time measurement, we want to also make sure that you are using one unit instead of, like, let's say 5 people, disagreeing on if it should be in meters or miles or feet and things like that. So that's why what we do here, we use SI units. So this SI unit, right, or the System International, so short SI, this is basically a system, or sometimes known as a metric system, right, where we take the length, mass, and time measurements in terms of meters, kilograms, and seconds, okay? So what we can see here is that then 1 second is defined as the time required for 9,192,631,770 oscillations of the radio wave absorbed by a cesium-133 atom. Right, so as crazy as it sounds, it's extremely accurate. So then we take the 1 second to be how long does it take for this atom to vibrate that many times. All right, so the SI unit for the length is in meters, okay? So 1 meter is defined as the distance traveled by light in a vacuum during 1/299,292,458 of a second, which technically this number is nothing but the speed of light, okay? Speed of light in vacuum. So 1 divided by speed of light is basically gives us, as a actual definition of 1 meter, okay? Now, you can think of 1 meter by imagining a meter stick. That's basically what 1 meter is. Generally, in this is the time when in class, I take out the meter stick and I show you what is a meter, 1 meter actually is. But, if you've never seen a meter stick, try to maybe, like, let's say, imagine, let's say, or you can just do the conversion from the, I don't know, a meter to, let's say, which is 1 meter is up approximately, let's say 3 feet, right? So 1 meter is about roughly, 3 feet approximately, right? Or 1 yard. Okay, so a kilogram until 2019 was based on a platinum iridium cylinder that was stored in Paris. But after 2019, it was changed, redefined in terms of then some kind of, physics constant. We call it Planck constant, as approved by the General Conference of the Weights and Measures. So again, so this is, you don't necessarily need to remember any of these definitions and things like that, but you can think of, like, let's say when you using 1 kilogram, we don't just, shoot, okay, so something is 1 kilogram. We actually we have some kind of reference. So that means, something, right, in terms of this Planck constant, is considered to be 1 kilogram. Something is double that value is 2 kilograms, 100 times more, 100 kilograms, and so on and so forth. So that's why what we do here is then the SI unit takes meters for the length, seconds for the time, and kilograms for the mass. And those are technically the fundamental units, Because, for example, velocity is meters per second, see, length per time. Acceleration is meter per second square, length per time square. Force, which is basically newtons, is nothing but kilograms meter per second square, which is, again, all in terms of these three fundamental units. That means everything in this class, Physics 220, will be in terms of, those three fundamental units. Yes, we're learning, let's say, force is, different quantity, but it's technically just another way of measurement of, like, let's say, mass, mass, length, and time, pretty much. All right. So as I already mentioned, everything in this class is going to be in SI units. That means you need to start learning, or visualizing what the meters, centimeters and kilograms, those are, let's say, are. And obviously it's not easy. So one of the things you can see here is this, this is some sort of, like, let's say, some useful conversions. Okay. So, sorry, let me kind of go back here. So some, conversions. 1 inch is 2.54 centimeters. 1 mile is 1.604 kilometers. And remember, 1 kilometer is 1,000 meters, right? And so on and so forth. So those are kind of like, let's say, 1 miles per hour is roughly half a meter per second. So that's why one of the things we can do here is, in the next slide, I have sort of like approximation for all of those values. So for example, 1 centimeters is roughly half an inch. 10 centimeters, about 4 inches. So let's say, that you can visualize, for example, 10 miles an hour, 20 miles an hour, 60 miles an hour, because you drive every day, 20, But what is, let's say, 10 meters per second? How fast is 10 meters per second? I don't know. Do you know that? I know, let's say, because I do conversion all the time, but do you know how fast is 10 meters per second is? Or let's say 20 meters per second. Can human move at 20 meters per second? Well, let's see. 20 meters per second, we can use this conversion, which is 1 meter per second is roughly 2 miles per hour. That means this is 20 meters per second is 40 miles per hour. Well, can human move at 40 miles per hour? I mean, some can, let's say, but obviously, it's much faster than humans, let's say, are capable of running, right? Same thing is example, if you take, for example, 35 meters per second, let me see. So yeah, definitely this is not correct. 35 meters per second is not roughly 20 miles per hour. Should be about 70 miles per hour. Because, each meter per second here is roughly, 2 miles per hour, right? So do that conversion, you should get, roughly 70. Not sure why I have 20 miles over there. But in any case, for example, 350 meters per second, is not reasonable for a car, but for example, it's reasonable for a bullet, for example, right? Because about roughly 700 miles per hour. So that's why sometimes you have to understand when you're given a problem and you're solving for unknown quantity, does it make sense or not? If you calculate a 350 meters per second for human speed, definitely you got something wrong. If you got, let's say, 5 meters per second for bullet speed, again, you probably did something wrong. So you have to kind of like, I have some idea of, what those values represent, because I've seen, sometimes in this class when people give me those values, I'm asking calculate the distance from, I don't know, from LA to, let's say, Las Vegas, they give me 10 meters. That's the distance, of your room from one end to the other end, but not from here to Las Vegas, let's say. So you have to kind of understand, most of you probably really well, visualizing miles and, let's say, feet and things like that, but you need to also get, comfortable with SI unit. One thing we have here is that's also very useful is the dimensional analysis. And dimensional analysis generally written, for example, if it's a speed, so you can see, right, as distance per time. So you can write as the length per time. Okay, so length per time, that's a dimensional analysis. So that's why this is useful when you're doing the equations. For example, here's an equation. Velocity equals, I'm giving like, let's say not the equation, velocity. So final velocity equals initial velocity plus acceleration times t squared. So let's say you have this equation. The question is, does this equation make sense or not? Because on the left side, what I have is a velocity. What is the units for velocity? Well, it's meter per second, which means it's length per time. So length over time. So that's the dimensional analysis of the left side of the equation. Let's look at on the right side of the equation. What I have here is, on the right side, I have velocity, which is in terms of length over time. That's fine. Then plus acceleration times t squared. Well, let's see what is the units for, what is the dimensional analysis for the acceleration? Well, remember, acceleration has the units of meter per second squared. Means it's length per times squared, right? Well, then times time. What is the dimensional analysis for time? Well, it's time squared. Now, when I'm looking at this, so this is length over time equals length over time plus length over time squared times time squared, which means that time squared and time squared cancels out. And what I end up on the right side is this, length over time plus length. Now the question is that, does it make sense? Can I add length over time, some kind of quantity which is length over time, to another thing that is length? Well, the answer is no, you cannot. You can only add two things that dimensionally match. In this case, length over time cannot be added to length. Those are like apples and oranges, okay? So one thing you can do here is you can add length over time to another length over time. How do we make sure that we had length over time? Well, remember, if this t squared was t instead, then what we would have had this t would have just canceled that t, square over there. Then we would have had L over T plus L over T instead of L over T plus L. That means the equation cannot be T squared. It has to be A times T in order for it to work. And that's something we're going to be seeing then in the next chapter. All right, so there you go. That's basically what I was, pretty much going over. All right, guys, so that's it for this chapter. So hopefully you'll have a chance to watch it before our next meeting tomorrow. And then we can talk about, to summarize this during the meeting.